Hello, we'll be talking about neural methods for personalized product search today. This high-level overview or survey of some recent papers has been structured into two sessions. One is more about what's the customer problem, what's the technical challenge, what's the solution approach. Then we will talk about this first session will be for 15 minutes. Then around for 30 minutes we'll talk about more details about motivational examples and also some qualitative results from experiments from these papers. So these are a set of references at a very high level. Basically, there's a lot of work from Amsterdam and also from University of Massachusetts and in Amherst under Bruce Campbell, and also some work from industry folks also. And some of the papers they may not go too deep. In fact, even though most of the methods are based on neural methods or deep learning approaches, there is a seminal paper from Urbana Champagne, Qingjiang Zhai. So we'll just start the presentation with that paper. So basically, what is coordinated intent representation, which was proposed in 2015? Just a minute. Is more like keyword queries retrieve entities based on structured attribute values. What we mean by that, unlike web search, which caters to information needs, product search reveals shopping preferences and ranks entities in a database in response to preference keyword query. Intent representation based on query space overlook connections with entities. Engagement log mining alone cannot fully discover user preferences. So probabilistic retrieval models in general leverage search logs to align product features with word descriptors in an earlier work by the same group under Qingjiang Zhai. While specific query intent can be transformed into data level representation in such approaches, popular user intent cannot be discovered in product search. So we need something more. So that's where this current paper makes a contribution in terms of a language model which captures query terms used for search, series of probability distributions on entity attributes and values, generative model for entities, sampling features on each attribute. It's thus better to leverage entity structure instead to infer what users actually look for in the target space directly, rather than just superficially understanding semantic meanings of queries as in past approaches. Proposed joint mixture model consists of word distribution to capture the user's choice of search terms. Example, as you can see at the bottom, like smart, right? And next, attribute preference distribution to capture its importance. An example is brand. Finally, feature value distribution for each attribute to reflect the user preference. An example is LG. Different intent models for the TV category vary across price and size, as you can see at the example at the bottom. So next, let's just talk about something which happened with Geisel in 2016, what is called as latent semantic entities. So basically, in product search, there's a mismatch between queries and representations. Different terms describe same concepts, resulting in vocabulary gap. So this discrepancy between buyer's shopping list and how retail stores maintain the information, that's the customer problem. So retrieval models on bag of words assumptions are less suitable to address this issue, as will be talked about in this paper. So the initial approaches were based on language modeling objective or heuristically constructed representation. So that's the technical challenge. These discriminative methods, such generative approaches or like compute full property distribution over entities. We need to avoid this rather with a discriminatory approach, and that's possible if there's enough training data. So what's the overview of such an approach? Um, Basically project a query and product into a high dimensional space. Thus, conceptual meaning can be directly matched and vocabulary gap can be avoided. The discriminative relation between a particular word and product through unidirectional mapping, distributed representation with gradient descent, and noise contrastive estimation to avoid probability distribution over all entities. Attribute level analysis of product search logs is focused on structured aspects of product entities. In contrast, learning separate distributed representation for words and entities from unstructured documents accompanying entities, as proposed in this paper, is a novel contribution. Latent features thus encapsulated by the model are shared by different concepts, and knowledge about one concept influences the others. So that's the kind of segue from more like language modeling or probabilistic retrieval model based approaches to neural methods to address the vocabulary gap, very much there in product search in particular. So next, let's just talk about hierarchical embedding model. This is from the group from Amherst, University of Massachusetts. So what's the customer problem here? Using topical relevance as a measurement of retrieval quality that ignores effects of users in online shopping. In web search, relevance is related to the query topic, whereas in product search, return result list accounts for the user's personal behavior. Not considering individual differences will not thus satisfy needs of all users. So how can we go about addressing this? Only a few items relevant to the query are purchased in product search. User opinion differs even on same product. As an example, a music CD. Personalization increases chances of showing products users might buy. So reviews thus provide information about both product properties and user preferences, which enable search engines to learn, understand, buyer taste better. Semantic meanings thus need to be captured across query, product, and user for personalized search on a new query. So what's the technical challenge? There is this query product user language mismatch. As an example, a TV review varies from camera description. Query dependent user model is unrealistic though, because there's not adequate training data for each pair. What is being proposed is query intent or user preference. You can explicitly control their weights and there is good compositionality for linear combination. So the weights are like lambda, and query intent is q, user preference is u. So that's how this model is formulated. So now user query pairs are constructed by linking user item pairs with each item's queries. Optimal query weight could be much lower than user weight on some product categories where personalization is indispensable. Central premise is that user preferences are independent of query intents. Next, we'll talk about attentive long short-term preference modeling from National University of Singapore under Professor Mohan Kankanayali. So buyer preferences which affect their current purchasing intentions. This bias which evolves slowly and the inclination in a relatively short period. So this is the key difference, long-term and short-term. Jointly models the choices for personalized product search. Short-term session data from web search, though it's too sparse for training. Profile-based browsing behavior alone does not reflect current context or recent choices. So instead, attention networks which distinguish these factors for current query are proposed. So you need to attribute some weights to constituent-wise impact, so that relevance of each factor, short-term preference in particular, fuse query and preferences to represent intention. pairwise learning to rank method for best ranking list. So both types of preferences thus model by attending to users' recent purchases and a global user vector with query. Model itself still conducts personalization all the time. So that is a handicap. So next we'll talk about zero attention model. So here search logs sample for personalization. So what's happening, some of the technical challenges, unreliable information adds to sparsity or noise. User information has extra feature in the retrieval model, and the profile is constructed in a query independent fashion, as we saw in the hierarchical embedding model. But in practice, query characteristics and there is interaction between queries, both need to be factored in for personalization. Let's look at some rationale behind such an approach. On the one hand, personalization with user information helps better understand search intent when there is limited information revealed in query. On the other hand, incorporating unreliable personal information could amplify data sparsity and introduce um, so the central question is, does personalization always improve product search quality? In particular, due to its negative effects on web search from a few previous studies. As an example, a customer may want results meeting their personal needs, sensitive teeth, for a query like toothpaste, or they don't differentiate much between returned results and simply purchase bestseller on the list. So what can we, when or how to personalize user query pair? No purchase history in new category, so that could be a problem. Usefulness depends on query context, interaction with previous purchase, maybe for spear phishing, same item is bought. So representing users' purchase intent with a convex combination between query user embeddings, as in hierarchical embedding model which we talked about earlier, applies undifferentiated personalization to all search sessions. Since combination coefficient is fixed number, constructing user profiles, thus with query independent information provides little insight on how beneficial personalization is. Knowing query and user purchase history simultaneously is necessary, as users' queries are dependent on each other, which however makes query specific personalization impossible. So that's the crux of the zero attention model. In the next session, we'll talk about more detailed example, then this concept will be more clearer. For now, we'll shift to the next paper. So the next paper is again from NUS. So here, what's happening is not just text mode, we should also take into account the visual mode modality in ranking. Like color, style, they are better expressed in the visual mode versus material and size in the text mode. So visual aesthetics in general influences conversion for clothing, shoes, such lifestyle category products. An example is like square versus round collar in t-shirts. So users could comment whether an apparel is comfortable to wear and worth buying. However, other aspects which can be directly viewed in product images are seldom mentioned in reviews. Personalized product search should thus rank products not only relevant to a query, but also match users' visual preferences at the top positions. So such visual cues could be leveraged to influence purchase in apparel or fashion category. Capturing multiple modalities is critical to understand customer preferences in a holistic fashion and preserve visual and textual similarity both of products shown in response to a query. That's the premise or crux of this particular paper, not just text modality, but also visual modality. Now we'll talk about dynamic Bayesian metric learning. So basically, you need to collaboratively track evolution over time, latent representation of different entities, users, and products in giant space. Probabilistic learning to keep the triangle inequality in latent space versus inner product for entity affinity. As an example, some items could go out of fashion due to better choices. Also, users' personal interest shift to another style. Prior work in personalized product search considers only static scenarios. User preference, product popularity, reviewer semantics, though change in due course due to better alternatives, like Samsung versus Nokia in cell phones from 2009 to 14, or Toy Story figurines in 2007, just before the movie release. Also, matrix factorization is not powerful enough to alleviate contradiction or violation of triangle inequality in relationships among users, products, and words. This limits fine-grained preferences and product or user-user similarity. Even RNNs don't model evolution of products and words. They only make predictions in the original observation space and don't learn compressed data representation. Thus, computationally heavy and lack interpretability, which in turn hinders the dynamic exploration. Instead, this paper proposes Gaussian mixtures for uncertainty. So basically, from static to dynamic scenarios, how do you capture user preferences? So that's the contribution of this paper. So next, we'll talk about transformer-based embedding. Personalized product search undifferentiated across sessions, either a fixed coefficient to control influence or an attention mechanism. So that's what happened in hierarchical embedding model and zero attention model. So what's the problem? So maximum personalization ZAM can perform is to equally consider query and the user information, which may not be enough when the user preference dominates purchase. In fact, in some cases, personalization could have a larger impact than queries. In contrast, the ZAM, actually ZAM does suggest effect allowing query to attend to a zero vector, at most as equally important as the query. Representation of items are static across collections, regardless of items co-occurring in user historical purchases. But transformer embedding model, in contrast, can learn to balance the influence of personalization for each query automatically without limits on the personalization degree. Specifically, the query weight can be as small as 0 when personalization is dominant, and as large as 1 when personalization is not needed. Uh, uh, Transformer embedding model thus is more flexible, where personalization can vary from no to full effect. A multiple layer term takes into consideration interaction between purchased item, so that it could learn potentially better dynamic representation of queries and items, which probably leads to better attention. So what are the unique aspects of the solution? Encoding query sequence for effect from 0 to domination, item interactions co-occurring in user purchase history, considered when computing attention rates. Since a recent purchase may play a different role compared with a long ago purchase, in addition to query and item embeddings of a corresponding unit, positional embeddings are also used to indicate purchase order of each item. Thus, query or items are dynamically represented depending on its interaction with other units associated with this query user pair, rather than static vectors across the corpus. By considering relationship between historically purchased items, as an example, same brands or categories, then thus could learn potentially better representation. So next we'll talk about embedding towers. This paper, this is the last in this survey. It addresses two aspects. One is query intent, other is personalized search. So semantically relevant items, but not exactly matching to the query terms. How do you capture them? So term mismatch between queries and items, where item titles are often short, is the critical challenge for e-commerce search. Rewrite, though, transforms the original query to another similar query that might better represent search needs. But limited rewrites can't retrieve items with different terms and preserve search intent despite rewritten queries. So that's the technical challenge. So what's the solution overview? Before we go there, in fact, different optimization objectives in candidate retrieval versus ranking. supervised model to optimize relevance metrics based on large-scale dataset with relevant signals, which is clicks and label annotation, versus unsupervised learning from word co-occurrence in documents, as we saw from prior approaches. So query and item embeddings are independent of each other after the model is trained, so they can be computed separately. All item embeddings can be computed offline in order to build an item embedding index for fast nearest neighbor search online. And query embedding can be computed online also to handle all possible user queries. Even though embeddings are computed separately, due to simple dot or instead of inner product interaction between query and item towers, corresponding embeddings are still theoretically in the same geometric space. Thus, finding k nearest neighbor items for a given query embedding is equivalent to minimizing loss for k query item pairs where the query is given. Multiple query embeddings can provide rich representation for queries intentions and capture different semantic meanings for a polysemous query. Example is apple, fruit, or brand. Different popular brands for a product query. Example is cell phone. Different product for the brand query. So example is Samsung. All these various intents can be captured and modeled using embedding towers. That's the claim. Right? Now, the other aspect of the same model is personalized search. Tailor to different users for the same search query. Retrieve items per user characteristics like gender, per user characteristics like gender and purchase power. A woman's t-shirt for a female user. Rule-based solutions use indexing tags for items, same as tokens into the inverted index. Building separate indexes for different groups is hard to meet certain needs with such handcrafted approaches. Inverted indexes cannot retrieve different items according to current users' characteristics. Instead, offline model training and indexing, online serving negative sampling, multi-head query item tower, dual encoder, and attention-based loss function. That's the salient features of solution for personalized search. Human-generated data can thus be collected based on domain knowledge as artificial negative query item pairs. Example cases are generated as negative items for query cell phone because they share similar product words literally, but differ significantly in semantic meaning. And positive query item pairs. iPhone 11 items are generated as positive items for query newest large screen iPhone. So that concludes the high-level overview with customer problems, technical challenges, and solution approach for the 6 to 7 papers we reviewed in this session. We will next move on to more detailed motivational examples and maybe some qualitative results. Thanks.